So, dear students, I welcome you for the today's lecture to revise the conduction. So, what is conduction? The particles that are going to move and are getting heated because of the differences in temperature. The particles that are very close together can transfer the heat energy as they vibrate. So this type of heat transfer, that is called the conduction. Conduction, that is the method of heat transfer in solids, but not liquids and gases, that is there. Mostly this conduction is associated in case of solids because of the vibrational energy, the heat that is transferred. Molecules, they actually vibrate, and because of that the heat is getting transferred from one end to the another end. So the flow of heat in a substance due to the exchange of energy between the molecules having more energy and molecules having the lower energy, that is the temperature difference is required to transfer the energy. Why the heat transfer takes place is because of a temperature difference, that from higher energy, higher temperature to the lower temperature the heat will transfer. So this transfer of heat from one particle of matter to the another by direct particle to particle contact, that is when the molecules they vibrate, they have the direct contact in between them, and which is possible in case of solids, the vibration heat that is getting transferred. So that is the rapid vibrating particles, they absorb the energy, collide with each other, then the metals are your good conductors. So coming to the basic equation, that is the Q, which is directly proportional to the surface area temperature difference and inversely proportional to the L. So proportionality constant, that is the K, thermal conductivity, K Q, which is equal to Ka into delta T upon L. So that is what Q is proportional to the time T during which the conduction takes place. The Q that is proportional to the temperature difference delta T. Q is proportional to the cross sectional area A, and Q is inversely proportional to the distance L. So this distance L that is to be taken, the cross sectional area A so that so in this conduction, that is the molecular vibration and free electron diffusion, both the things are important. Molecular vibrations and the diffusion that is there. So direct, it is a direct transfer of the heat. When touching or direct contact, the faster molecules, the warmer temperature, that is the molecules, as the temperature is higher, the molecules will have the higher kinetic energy, so they will vibrate at a higher rate, and as a result the transfer will be the higher. So your equation, that is, we are having the Fourier law, this law that is called as the Fourier law, that is heat transfer rate Q, which is equal to minus Ka dt upon dx, which is having the units of watt. Watt is nothing but the joules per second. So this is area and the temperature difference and the distance difference. So dt upon dx, that is mentioned as the temperature difference and the distance difference. A is the cross-sectional area, K is the thermal conductivity, which is having the units of watt per meter Kelvin. And this Q double dash, which is nothing but the heat flux. Now this A is taken on this side, so this will become equals to Q by A. So Q by A, this is nothing but your heat flux, that is the heat transfer per unit area. This is nothing but the heat flux, heat transfer per unit area. That is what the unit will become watt per meter square. Watt per meter square, because we have divided this by area. So the thermal, and this law is called the Fourier law of heat conduction. Now the thermal conductivity K is a measure of the ability of material to conduct the heat. It is the measure of the ability of a material to conduct the heat. dt upon dx, it's a temperature gradient. So the rate of heat conduction to the solid is directly proportional to its thermal conductivity K. Now consider this slab, which is having a certain temperature of 30 degrees Celsius on one end. On the another end, its temperature is 20 degrees Celsius. Heat is transferred from higher temperature to the lower temperature. This is what the heat flow that will be there. And that will depend on the cross-sectional area A and the thermal conductivity K. Now this is the copper, which is having a thermal conductivity of 401 watt per meter degree Celsius, and the silicon, which is having thermal conductivity of 148 only watt per meter degrees Celsius. Now the temperatures are same, the width is also same. However, the amount of heat transfer, that will be the different. The Q, which is 4010 watt per meter square, and the Q in case of a silicon, that is 1480 watt per meter square. This is only because of this K thermal conductivity. The K for the copper and K for the silicon, they are different. That is what K is the measure of the ability of material to conduct the heat. When the thermal conductivity K is higher, it is easy for the material to conduct the heat, and as a result, the rate of heat transfer is also high. If the ability of a material to conduct the heat is high, that is, the thermal conductivity K is high, as a result, you will get the higher heat transfer rates. Then, this is the rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. Now the K, thermal conductivity, how that is defined? The same Q, which is equal to Ka into delta T upon the L. I am writing now this in terms of the K. So this K is defined as the rate of heat transfer Q through a unit thickness of material, that is L, unit thickness of a material, or you can say the delta X also, the distance between the two ends. So this is the rate of heat transfer through a unit thickness of material per unit area A, per unit area A, per unit temperature difference. This is what the K thermal conductivity that is defined. Thermal conductivity of material is the measure of the ability of a material to conduct the heat. A higher value of thermal conductivity indicates that the material is a good heat conductor, and a low value of K indicates that the material is poor heat conductor or the insulator, that is also called the insulators, where they provide the less thermal conductivity. Diamond, that is having the highest thermal conductivity of 2300 watts per meter degree Celsius. Below that, silver, copper, gold, aluminum, all these are your metals. Now come to the wood. Wood, water, that is having the thermal conductivity of 0.6 watt per meter degree Celsius. You have to remember this for the water. Water and the air also, you can remember it. Air, that is 0.026 watt per meter degree Celsius. So this thermal conductivity of gases such as the air vary by a fraction of the 10 to the power 4. Pure crystals and metals have the highest thermal conductivities, and gases and insulating materials the lowest one. So from this figure you can see that all the metals are having the higher thermal conductivities, water is there, and then the gases below that. So gases are in the point up to 0.1. Now the thermal diffusivity, that is nothing but the K upon rho Cp, that is the heat conduction upon the heat storage. Cp is your specific heat, which is having the units of joules per kg degree Celsius, that is the heat capacity per unit mass. Rho Cp, when you multiply this specific heat, it becomes your heat capacity, because you are taking into account the mass. That is what? The heat capacity. The heat capacity per unit volume it becomes when you multiply specific heat with the help of a density. Now the thermal diffusivity is having the units of meter square per second, represents how fast the heat diffuses through a material. How fast the heat diffuses through a material. The material that has a higher thermal conductivity, that means higher value of the thermal conductivity, or the lower heat capacity, will obviously have the large value of thermal diffusivity. K is high and lower value of Cp. If both are high, then that will be around 1. Both are low, then that will be also around 1. But if the thermal conductivity is low and the Cp values are high, then the thermal diffusivity will become low. So you have to remember, numerator values should be higher. That is the K upon rho Cp. A material that has a higher thermal conductivity or a lower heat capacity will obviously have the large thermal diffusivity. Thermal diffusivity, that is the ability to disperse the heat. How effectively the heat that can be dispersed inside the material. A smaller value of thermal diffusivity means that the heat is mostly absorbed by the material and a small amount of heat is conducted further. Absorb तो हो जाता है, but it is difficultly conducted, transfer from one place to the another. So we can have these small problems that can also be asked in the examination. because I have put these small problems related to your basic equations, that is Q which is equal to UA delta T, Q which is equal to HA delta T, Q which is equal to KA dt upon dx, Q which is equal to M lambda. These are your basic four equations that are needed in case of your heat transfer. Now remember that which equation is to be applied at what condition, that is also important. In case of a conduction, that is Q which is equal to K delta T upon delta X. Now in this case, that is okay. Now coming to the steady state heat conduction in the plane wall. So heat transfer through the wall of a house can be modeled at steady state one dimensional. The temperature of the wall in the scale that is indicated on this end, it is 20 degrees Celsius, on this end it is 3 degrees Celsius. So the rate of heat transfer into this wall minus the rate of heat transfer out of this wall, which is equal to the rate of change of energy of the wall. Input minus output, that is going to give you the change. Change of what? The change of energy across the wall. So this is the rate of heat transfer into the wall, which is indicated by Q in, minus the rate of heat transfer out of the wall, that is nothing but the Q out, which is equals to the rate of change of energy of the wall, that is dE upon dt. In steady operation, the rate of heat transfer to the wall is constant. This is very important. In steady state operation, the rate of heat transfer through a wall or through a sphere or through a cylinder or through any object, that will remain constant. But condition is that it should be the steady state operation. Then and only then the rate of heat transfer is constant. Generally, we are taking all the problems at steady state condition. When we will discuss related to the practicals, we allow certain time to attain the steady state. So initially it is at a lower temperature. We start the heating, and once the temperature starts building, it attains the steady state value. What is steady state value? That is change in temperature with respect to time, that is 0. Change in temperature dt upon small dt, that is the time. Change in temperature upon change in time, that value is 0. That is nothing but your steady state operation. So the rate of heat transfer, that will remain constant at steady state. And our Fourier law of heat conduction, which is minus K dt upon dx. Now there are certain resistances that can be taken, and these are the thermal resistances. Our basic heat conduction equation, Q which is equal to K minus Ka dt upon dx, right? Minus Ka dt upon dx. After integration of this, you will get Ka into T2 minus T1, and minus sign is manipulated so that it becomes T1 minus T2 upon the end. So this is our heat conduction equation after the integration. Now this is the temperature difference, and rest of the things that is constant, that is L upon Ka. So this L upon Ka, that is called the wall resistance. This is the resistance that is through the material. That is the conduction resistance of a wall. Thermal resistance of wall against the heat conduction. And this thermal resistance of medium depends on the geometry, and these thermal properties of that means your thermal conductivity. K and L that is associated with a geometry and the width, and the thermal property that is the K, thermal conductivity. Then in case of a liquids, there is a Newton's law of cooling, which we are having the equation Q, which is equal to HA into delta T, where Ts is the surface temperature and T infinity is the atmospheric temperature or the infinite atmospheric temperature. That means from surface to the atmosphere, what is the temperature difference? HA, that is called the convective resistance, R convection, which is equal to 1 upon HA. Now, in this case, it is the metal wall that is taken into account and the resistances because of the air film that is taken into account. Air film on this side, air film on the another side. So T infinity 1 is the surrounding temperature on one side, T infinity 2 is the surrounding temperature on the another side. So this is what, say assume that this is getting heated at a higher temperature. That is why it's a T infinity that is mentioned. So from this temperature gradient T infinity 1 to T1, that is we are doing calculations now, T infinity 1 to the T1, this is what the resistance that has been taken into account, and this is called the convective resistance. This is a conductive resistance, that is because of the metal wall which is offering. Again, this is the convective resistance because of the gaseous film. This is also because of the gaseous film. So this is the convective resistance T infinity 1. That means the temperature gradient across the T infinity 1 and the T1 upon 1 upon H1A. Now H1 is your heat transfer coefficient on this side. H2 is your heat transfer coefficient on the another side. So that was with a one wall. Now we are assuming the two walls. So wall 1, wall 2. Now here the thermal conductivities are K1 and K2. H1 is the convective heat transfer coefficient. H2 is the convective heat transfer coefficient. Temperatures are T1, T2 interface temperature, T3 outside temperature. T infinity 1 that is at a higher temperature, so heat will transfer from the higher temperature to the lower temperature. And the widths are L1 and L2. So the first resistance that is taken into account R convective, which is equal to the 1 upon H1A. R for the wall, that is L1 upon K1A. R2 that is L2 K2A. That is what? From conduction equation, Q which is equal to Ka dt upon dx or dt upon L. So L upon Ka is your resistance that has been taken into account. And R2 convective is because of the gaseous film. So total resistance, when we take into account that is associated with the temperature T infinity 1 and the temperature T infinity 2. That is what is the total resistance we have taken into account, T infinity 1 and T infinity 2. So all the four resistance that is to be taken into account. This is first resistance, this is second resistance of metal wall, the third resistance of a second metal wall, and the fourth resistance of a liquid gaseous film which is on the other end. So R total is the R convective 1, R convective 2 and R wall 1, R wall 2. So this can be added. So we can have the heat transfer through all the resistances that will remain constant. Q that remains constant. If you do the calculation related to the T infinity 1 and T1, amount of heat transfer that will be same. If you will do the calculation associated with the T1 and T2, there also your value of Q that will remain same. Now, in this case, T infinity 1 and T2 calculations we are doing. T infinity 1 and T2 calculations we are going to do. Right? So, first resistance and second resistance, only two resistances that will be there. Now, if we will take T infinity 1 and T1, then only one convective resistance will be there. So, this is what? Q, which is equal to T infinity 1 and T1 upon the R convective. यहाँ पे सिर्फ R convective काउंट होगा. T infinity and T2, there is R convective plus the wall conduction. So two resistance that is taken here. Then T3 and T infinity 1, there the three resistances that will be taken into T infinity 1 and T3 if there is. So first resistance is because of the conduction wall and wall convection. Now on the another side, now I can take T infinity 2 and T3. So T infinity 2 and T3, there I can consider only the convective resistance because of the gases. So only R convective that has been taken into account. I can also do the calculation associated with the T infinity 2 and the T2. That can also be done. So what is the data, which data is available with me? Based on that, I am able to calculate the temperatures. To find the temperature T1, to find the temperature T2, to find the temperature T3. So depending on the end temperatures and depending on the resistances, I can calculate, depending on the amount of heat transfer Q, if I know this Q, and I can calculate the individual temperatures. So this is very important application of this. I can calculate the temperature at any point. Say this is 500 degrees Celsius and this is 30 degrees Celsius. So I have to decide what should be the K or what should be the width of this wall. Then coming to the long cylindrical pipe or the spherical shape. The same equation Q, which is equal to minus Ka dt upon dr. However, this K in this case is going to vary. Now as it's a cylinder, this K that will be equals to the 2 pi r into the L. If it is a wall, then this area that will be is equal to length into the breadth, length into the thickness through which it is going to pass. Then the integral from K T1 to T2. Now this is the temperature T1 and it is going to the temperature T2. So integration from T1 to T2 from radius R1 to the R2. So after integration and simplification, Q for cylinder, which you will get as 2 pi KL into T1 minus T2 upon ln of R2 upon R1. Now in this case, what will be the resistance? T1 minus T2, that will be there, and R resistance, that will be nothing but ln of R2 upon R1 upon 2 pi KL. So this is what? Resistance through the cylinder that is mentioned. This is the conductive resistance of a cylinder layer. That is ln of outer radius to the inner radius upon 2 pi KL. Now in case of a spherical shell, what will be there for the spherical shell? Your equation that reduces to 4 pi R1 R2. So this area of a sphere, that is going to change. This is the area of a cylinder. You have to take the area of a sphere, and similar steps you can do this simplification, so that conduction through the sphere, that will be equals to the temperature difference upon the R2 minus R1 into the 4 pi R1 R2 into the K. So in case of a cylinder, what will be the resistances now? The first resistance is the inner convective resistance, then the cylinder metal wall resistance, and third is the outside convective resistance. Again here T infinity 1, T infinity 2, T1 is the surface temperature, T2 is the outer surface temperature. So the total resistances, when you take into account this temperature difference T infinity 1 and T infinity 2, T infinity 1 and T infinity 2, the R total that will be accounted, and this R total is the first R convective, R cylindrical, and R convective 2. This is R convective, that is 1 upon H into the A. Area will be 2 pi R into the L. R1, this is the inner surface area, is having the H1. R1 is associated with the H1, inner surface area. And similarly R2, that will be related to the outside heat transfer coefficient H2. H2 corresponds to the R2. And in case of a sphere, this becomes equation 1 upon 4 pi R1 square into the H1 plus R2 minus R1. This is also related to the R convection, R for sphere, and this is R for convection. Now in case of a multiple cylinders, that is, we are considering the 3 layers 1, 2 and 3, having the thermal conductivity is K1, K2, K3, radius R1, R2, R3 and R4. H1 is the inside heat transfer coefficient, H2 outside heat transfer coefficient, T infinity 1 and T infinity 2. So the temperature gradient of T infinity 1 and T infinity 2, that will be your total resistance. You can do also calculation related to T infinity 1 and T2. So individual T2, that can be done, T infinity 1 and T3, that can also be done, T1 and T3, that can also be done, T2 and T4, that can also be done. Any permutation and combination that can be done. However, remember that in between those two temperatures, what are the different resistances that is to be taken into account? कोई भी लो permutation combination, T infinity 2 and T4 लो up, so only one resistance will be there. Or to calculate the T4, I can take the T infinity 1 and T4. That can also be done. But when you take T infinity 1 and T4, My resistances are R convective 1, R cylindrical 1, R cylindrical 2, R cylindrical 3. 4 resistances I have to take into account. However, if I will take the T infinity 2, I will have only take into account the one resistance. वो कौन सा रेजिस्टेंस है, कन्वेक्टिव रेजिस्टेंस है, कंडक्टिव रेजिस्टेंस है, दैट इज टू बी स्टडीड. So we will discuss now related to the three-dimensional equation. So fundamental equation of the heat conduction, that is Q, which is equal to minus K dt upon dx. Now we will consider or calculate the general heat conduction equation. We are assuming the metal cube through which the heat flows in the x direction, heat goes out from the x direction. In the y direction, heat is going in, heat is going out. In the z direction, that is across the z plane. So the heat into the element, the net heat conducted into the element plus the internal heat generated, which is equal to the increase in the internal energy per unit time plus the work done by the element per unit time. Net heat conducted into the element, that is the input minus output, plus the generation term or the consumption term that will be there, generation or consumption, and the changes in the internal energy, increase in the internal energy per unit time. This is what the unsteady state term that will be there. And based on that, what will be the work done by the element per unit time.